Okay, today we're going to talk about perimeters and areas of similar figures, and these are two-dimensional figures. So we want you to learn to find the perimeters and areas of similar figures. And this lesson is going to be a little bit different than some of the other lessons because there is an investigation that I want you to do. So look in your book at page 454, and there's an investigation on that page that I want you to do. It's in blue on that page. So I want you to stop this video and perform the investigation on your own. Now this investigation is considered part of your notes and it will be checked as part of your in-class exercise, okay, that we're going to do when we come back together with this, okay? So make sure that you perform this investigation, stop the video. Your investigations will all look different from each other, but that's okay. Okay, now that you performed the investigation, what you should have discovered is that the perimeters and areas of similar figures have different values that we can associate with them. Okay, so if our similarity ratios between two figures is some number, sum A divided by B, then the ratio of the perimeters of the two figures will also have that similarity ratio, and the ratio of the areas of similar figures will have the ratio of that original similarity ratio squared. Okay, so let's take a look at what this means. Here's our example problem. We have two regular hexagons, which means they're similar hexagons, and they're going to have similar side lengths of 6 centimeters and 10 centimeters. We want to find the ratio of their perimeters and areas, as well as both of those values for both hexagons. So let's start with the 6 centimeter hexagon first, which if we divide that in half to account for our apothem, we'll have 3 and 3 radical 3 because of our 30, 60, 90 relationship within this little triangle here, which means that our area, which is going to be used ASN over 2, should be apothem, which is 3 radical 3, times our side length, which is 6, times the number of sides, which is 6, all over 2, should be, let's see, 54 radical 3 centimeters squared. Okay, now our perimeter should be pretty easy to figure out. For the 6 centimeter hexagon, it'll be 36 centimeters, and for the 10 centimeter hexagon, it will be 60 centimeters. Now we can use the ratio of our perimeters to find the similarity ratio between the two hexagons. Of course, you could also look at it with just the side lengths as well, and that would form a similarity ratio of 6/10, right, which is just 0.6. Okay, so now actually I shouldn't say 6/10 really. It's a similarity ratio of 6 to 10, right? Which if we're creating a bigger hexagon is actually going to be 10 over 6, which is divided by 2, which is 5/3, right? Okay, so when we find the area of our new hexagon, we could go through all the rigmarole of, ASN over 2, or we could take this 54 radical 3 and multiply it by 5/3 squared. So 54 radical 3 times 25/9 will just give us 54 times 25 divided by 9 will give us 150 radical 3 centimeters squared. So my similarity ratio is 6 to 10. So if I'd found the area of the bigger hexagon first, I would have wanted to multiply the bigger hexagon by 6/10 squared. Since I found the area of the smaller hexagon first, I multiplied it by 10/6 squared, which is 5/3 squared. I hope that makes sense to you, how to get from bigger to smaller and smaller to bigger. Okay? So the ratio of the perimeters to each other was 6:10. Ratio of the perimeters. But the ratio of the areas was actually, which could be 3 to 5, would be 9 to 25. Okay? So, I hope that makes sense to everybody. There's a couple different ways of expressing it. When we express it sideways like this, it lets us know which one's the bigger and which one's the smaller, and then we can use a similarity ratio either as 3/5 or as 5/3, depending on what we need to do with that similarity ratio. So let's look at another example. Here we have two regular nonagons, 9-sided figures, whose side lengths are 2 inches and 6 inches. The area of the smaller nonagon is 24.7 inches squared. And we want you to find the perimeter and area of both figures. Okay? So, the area, we don't know how to find the area of a nonagon if we don't know anything other than the side length right now. So we can use the fact that we know one area to find the area of the second one using our similarity ratio. Now the perimeters are fairly easy because 2 times 9 is going to be 18. And 6 times 9 is 54 centimeters. Now our similarity ratio is going to be 2 to 6, or 1 to 3, right? So since I know the area of my smaller nonagon, I can multiply that by 3 squared. So 24.7 gets multiplied by 3 squared to get the area of the larger one. So 24.7 times 9 will be 222.3 inches squared. Will be the area of my larger nonagon. So these ratios between the perimeters and the areas are really nice to note. Now, if we look at 18 and 54, the ratio between them should be 3 to 1, right? So the smaller times 3 should equal the bigger, and 18 times 3 does equal 54. So we know that we've got everything all right with that. Now let's take a look at two similar figures, okay? And we don't know anything about these similar figures other than they're similar and we know their areas, okay? So the area of one of them is 20 centimeters squared and the area of the other is 45 centimeters squared. So we want to be able to find the similarity ratio between them, okay? And the similarity ratio between the two figures. Actually, we're not going to be able to find the perimeter of the figures because we don't know anything about the figures. So we just want to find the similarity ratio between the two figures and the similarity ratio of the perimeters. We won't be able to find this. So looking at 20 to 45, 20 times some similarity ratio squared should equal 45, right? So this ratio squared should equal 45 divided by 20. And that reduces down to 9/4. So what squared is 9/4? Well, that A over B should equal 3/2, right? So if we knew the perimeter of 1, we would know that 3/2 we knew the perimeter of the smaller one, that we knew that, then we know that 3/2 times the perimeter of the smaller one equals the bigger one. Okay, so the ratio of the perimeters is going to be 2 to 3, smallest to biggest. Okay, but it also is a similarity ratio between the two figures. So again, hopefully these problems are helping you realize how to work with similarity ratios, and the back and forth nature between smallest to biggest and biggest to smallest, and how those are reciprocals of each other. So what we've learned the ratio of the perimeters between two similar figures is the same as a similarity ratio. We've learned that the ratio of the areas between the two similar figures is the same as the similarity ratio squared. And given either two areas or perimeters of similar figures, we can find the remaining data usually, as well as the similarity ratio. Now it all depends, we may not be able to find area or perimeter just given one or the other, but we can always find the similarity ratios between the two.